tipping points in our diagram, they don't really follow one particular one of these modules. They're kind of sitting outside in between our influence of temperature and the downstream impacts of temperature. So I just put them here in between these two modules because it's kind of how temperature impacts things that are downstream from temperature. So first of all, why are we talking about tipping points in the climate system? So there's a couple of major motivations for doing this. So motivation number one would just be that they're potentially very impactful. So we'll talk more about what these actual tipping points are, and you'll see how impactful they could be for the influence of greenhouse gases on various things that we care about. But also they've really penetrated into the forefront of the contemporary discussion on global warming. And so we can see that, for example, with statements from Greta Thunberg, who's probably now the most prominent climate change activist or climate action activist. So she gave this famous speech to the United Nations. And in it, she definitely talks about themes from related to tipping points. So she says the popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees. So she's kind of saying there's a threshold there. And the risk of setting off irreversible chain reactions beyond human control. So that's a theme that's part of tipping points. 50% may be acceptable to you, but those numbers do not include tipping points, most feedback loops, additional warming hidden by toxic air pollution, or aspects of equity and climate justice. So the idea of tipping points is now kind of at the forefront of communication on climate change. So stepping back, like what actually are tipping points? So first of all, it's interesting to look at like where the term actually came from. So it originated in industry in the 1800s, and kind of ironically, actually, it was first used in relation to coal cars or coal carts. So when you would mine coal, you put it in these carts that then when you want to get rid of your coal, you tip over the cart. And so the tipping point, of course, is the point at which the bucket tips over. And so you can think of like, you know, when you're right at that point, all you need to do is give it just a little bit of a nudge, and then you tip over into a new state. And then we also have this idea of tip buckets in various industrial uses. And one way that this is used is in rain gauges. So in the Department of Meteorology, we have a bunch of these lying around. These are tip bucket rain gauges. And this is how we measure how much it rains. Usually these are about 1/100 of an inch of rain. So as the rain comes in, it fills up a bucket, it tips over, that activates a magnet. And then it's just gonna count, okay, that was 1/100 of an inch, next time it tips over, another 1/100 of an inch, etc. And so that, again, it's this idea of like nothing is changing, and then all of a sudden you get this big shift, this big change. So the term tipping point, although it originated back in the 1800s, really went kind of full force into popular culture, popular vernacular, after this book, The Tipping Point, came out in the year 2000. So this is a book by Malcolm Gladwell, who's one of the most successful nonfiction authors of the 20th and 21st century. And so a lot of his books have had a very wide social influence. And so this book really helps the idea of tipping points come into the forefront of kind of the public's mind. And in this book, he looks a lot at kind of social phenomena like fashion, for example. So one of the main examples that he uses is to define what a tipping point is the sudden increase in the popularity of a particular shoe brand in 1995. So he was looking at the shoe brand Hush Puppies. and why they surged in popularity all of a sudden in 1995. And then another phenomena that he looks at is the sudden decline in New York City crime in the 1990s. So obviously, since this book was written in 2000, he's looking at kind of recent examples of abrupt shifts. So this was this is a graph of number of murders in New York City by year. It was relatively low in the 50s, and then it climbed up in the 60s and 70s, and then we had this dramatic decline in the 1990s, and then decline since then as well. So the tipping points that Gladwell talks about can be kind of described by this term social contagion. And so this is what he says about kind of the thesis of this book. Is the tipping point is the biography of an idea. And the idea is very simple. It is the best way to understand the emergence of fashion trends, the ebb and flow of crime waves, or for that matter, the transformation of unknown books into bestsellers, or the rise of teenage smoking, or the phenomena of word of mouth, or any number of other mysterious changes that mark everyday life, is to think of them as epidemics. So obviously very topical to what's going on in the world right now. Think of them as epidemics, ideas and products and messages and behaviors that spread like viruses do. So it's this idea that one person, you know, has some notion or has some idea or is displaying some fashion trend or some behavior, and then someone else copies them, and then that just spreads throughout, you know, some population. And he uses three characteristics to define tipping points. So he talks about contagiousness, so from one person to the next, and then the fact that little causes can have big effects, and that changes happen not gradually, but in one dramatic moment. And so this is, I will use this as kind of the public understanding of what tipping points are, and then compare that to climate tipping points, which turn out to be a little bit different. So just summarizing that in different words, tipping points exhibit rapid shifts between multiple states. So for example, a state in which an infection or a behavior is rare to a state in which it's widespread, that it's not just gradual, it's all of a sudden you're switching into a new state. And then, yeah, the scale and the speed of the shifts, how large they are, they result from some type of a positive feedback, some type of a reinforcing mechanism. And so in the case of humans, that often gets called network effects, right? Like the social network, so that you can kind of have dominoes tipping through a network of people, and something going from being very small to very widespread in a short amount of time. And so one kind of technical definition of that is that the abundance of a contagious element increases the rate at which it spreads, which further increases its abundance. So that's kind of the idea of this exponential growth that we talked about when we were talking about the virus and climate change, and just how quickly exponential growth, you know, how powerful exponential growth is and how quickly these numbers get out of hand. So, you know, we were talking about viruses before, but now we're kind of more talking about viral ideas spreading. And this is just this quick, you know, illustration of how powerful doublings are in terms of how many numbers or how big your numbers get, how quickly. So this is if one person gives an idea or a virus to two people, then you're at 2. After one iteration, then you're at 4, then you're at 8, 16, 32. By 64, you're already off this chart. And then you can see by 19 iterations, you're at over 500,000. At 20, you're at 1 million. At 30, you're over 1 billion. And at 33 iterations of these doublings, you're over the population of the planet. So it doesn't take much if something is spreading virally for it to be very, very widespread very quickly. And so it's interesting that this book, The Tipping Point, was written before a lot of what we now consider the internet even existed, right? So the internet is dominated by things that have tipped. And this book was written in 2000, so that's before Facebook, before Twitter, before YouTube. There was MySpace, I suppose. So that would be one way for ideas to go viral. But so then this book, if it was rewritten today, would probably have a lot of internet themes on it. So it would talk about like viral videos. So like Gangnam Style is an example of a video that certainly was viral in terms of it wasn't like imposed from the top down on people. Hey, everybody watch this video. It was passed from person to person. And you can see that it has over 3 billion views, 3.5 billion views on YouTube. So approaching half the population of the planet. Obviously not everyone watches at one time, but just compared to the population of the planet, it's half the size. So that's huge. And the most viewed video on YouTube, I just looked, is Despacito, which has more than the population of the planet. So it's like 9 billion views. So that's pretty incredible for some component of culture to spread that wide. And so we see this, not just with things like viral videos, but with apps. So TikTok has been blowing up recently. And then, we see this, like how much it can then affect the real world, that apps like Lyft and Uber, at first have very little penetration, very few people are using them, and then all of a sudden they tip, and then everyone's using them, and then all of a sudden taxi cabs are out of business, and then airports look different, and you're supposed to go to these rideshare locations. And so that's definitely something that's tipped because of the internet. And then things, on Twitter, memes, hashtags. Twitter is designed to have things go viral and to have things tip, right? So this retweet button is literally that in action, where someone says something, and then if someone else retweets it, it shows up on all of their followers' timelines as if that person had tweeted it. And so people with large influences on Twitter, it's like changing this base number. Instead of doubling, like you could have this be like 100, right? So if you have 100 followers and all 100 followers retweet your tweet, and all of them have 100 followers, then it's, instead of it passing it to 2 people, it's 100 each time. And so then that would be, or 100 raised to the power of whatever iteration you're on. And so that would be even that much more powerful. And that's how we've seen ideas like, like Me Too and Black Lives Matter. These were hashtags that started off with just a very few number of people and then went viral through this kind of retweeting exercise. And then all of a sudden everyone knows what those phrases mean. And so those are ideas or memes that tipped. So now I want to compare this kind of general notion of tipping points, which I think is exemplified by these Malcolm Gladwell type tipping points, to the climate tipping points that we're going to be talking about today. So the tipping point book version of tipping points in the climate system is this paper, this 2009 paper by Timothy Lenton and others. And so this really laid out the groundwork or the framework for how to think about tipping points in the climate system. And so these tipping points, interestingly, have some fundamental differences with what I'll call Gladwellian social tipping points. So just kind of first to look at what their definitions are. First, instead of defining a tipping point, they first defined a tipping element, which is just some component of the climate system. And they have this spatial part of the definition. It has to be subcontinental or larger, meaning like, the size of India, for example. So it has to be subcontinental or larger. And it's an element in which you can get these threshold responses, or something where a little cause has a big effect. So that's that's a definition, that's a component of the definition that's similar to the Gladwell tipping points. And then the tipping point is the critical threshold at which the small change in forcing, like a change in temperature, would trigger the disproportionate response, like, for example, ice melting. And under this definition, this is one of the major differences, is that crossing a threshold in the climate system commits us to a change in the long term, but it doesn't necessarily happen all at once. So it could take centuries or even millennia to be realized. So the tipping point is crossing the threshold, and then maybe you've committed to something very, very far into the future as far as human timescales are concerned. And then the change might also be irreversible. So irreversible is another part of this definition, or at least it can be. So the change, that's kind of like an amendum, is that the change also may be irreversible, but it doesn't have to be. So if we look at these definitions, or these descriptions of tipping points in the climate system compared to the Gladwell ones, basically they don't talk anything about contagiousness, right? So you're not spreading through a social network or anything like that. So that's out of the definition. And then it's not the case that they that they happen all at once in some dramatic moment, at least on human timescales. Maybe on geologic timescales, these could be considered abrupt. And so it's really just this single element that they share in common. Little causes have big effects. And so we'll focus on that component when we talk about these tipping elements in the climate system. One other thing about this paper that is important to note is that these tipping points in the climate system are very speculative. So they're not like well-defined points that science, quote unquote, knows exactly where they are, and that we are, ready to say, okay, we're this far away from this point and we know exactly when it's going to happen. And then once it does, this is what's going to happen. It's really much more speculative and cloudy than that. And so this is kind of exemplified by this passage in this paper, that it says, many of the systems we consider do not yet have convincingly established tipping points. Nevertheless, increasing political demand to define and justify binding temperature targets, as well as wider social interest in nonlinear climate changes, makes it timely to review potential tipping elements in the climate system under anthropogenic forcing. So they're basically saying that, there's calls to keep global warming under certain thresholds. And so because of these calls, it's a worthwhile exercise to kind of brainstorm about where there might be tipping elements in the climate system. So that's a little bit different than thinking about it like science has established tipping point X, Y, Z. It's more, this is just the reality, is that we really don't know about a lot of these. And so these are kind of just brainstorming exercises. And so going along with that, it's important to note that the Paris Agreement targets of keeping global temperature below 2 degrees above pre-industrial values, or below 2 degrees total of global warming, and or below 1.5 degrees total of global warming. These targets are international goals, but they're not well-defined tipping points in the climate system. And so that was a major point of confusion when this IPCC report came out in 2018, this was a report on the impacts of global warming at 1.5 degrees Celsius. We're currently at about 1. So with an additional 0.5 degrees Celsius, what are the impacts? That was what this report was about. And a lot of the media coverage was something along these lines. So this is a headline from the New York Times. It says, a new climate tipping point. And they're covering this report coming out, and they're acting like 1.5 degrees Celsius is some tipping point in which you switch into some new state. And that's really not the case. So this report was just about the impacts that you get at 1.5, not that you switch into some new state at 1.5. And actually, when scientists have looked at this in detail, looked at the climate models and looked for various points at which you might tip into a new state, they don't find any global temperature at which that happens. So this is just an example of a paper that looked at something like that. It says, well, the title of the paper is Catalog of Abrupt Shifts in Climate Models, essentially. And they say, we find no compelling evidence for a general relationship between the overall number of abrupt shifts and the level of global warming. So we know, and we'll talk about today, that there are various elements in the climate system that might tip at various levels of warming, but there's not some one global temperature at which we expect everything to spiral out of control or something like that. And that's all this is saying. So yeah, not one single established level of global warming that can be considered a tipping point. But having said that, we do know for sure that there are components of the climate system that act very non-linearly and very much like this threshold response, where you push it, it doesn't do anything, and then all of a sudden it changes very dramatically, kind of the straw that broke the camel's back type of thing. And so one example of that, I'll just show, you don't need to know the details of this, it's just establishing that we know that these things exist. So one example of this is called a Heinrich event, or a Dansgaard-Oeschger event. And what this graph is showing is essentially how warm it is at the top of the Greenland ice sheet. And this is going back 80,000 years before the present, 60,000 years before the present, 40,000 years before the present, 20,000 years before the present, and then present day. And so this is our relatively stable Holocene climate period. And then as you go back in time, you see these dramatic spikes, and they're numbered in this graph. And so one thing we know, these are very large temperature changes at the top of Greenland. And one thing we know is that there's not some external forcing that like really explains these temperature changes. So we know that this is somehow a redistribution of heat in the climate system that's being, that must be relying on positive feedbacks or some mechanism where you have a threshold response, where you don't have a proportionate response to your forcing. So we know that this is some type of like a tippy-like element of the climate system. And so this is just to say that we know these things do exist in the climate system, and it's clear in the geological record that we have things that are nonlinear and thresholdy and tippy. Okay, so this irreversible component is worthwhile to talk about a little bit more. So I'm going to compare two different notions of the response of something to an amount of global warming. One where you have a threshold, but the threshold is reversible. And then one where you have a threshold, but the threshold is less reversible, or perhaps irreversible on human timescales is another way that gets put. So a graph that would have a threshold that's reversible would look something like this. And I'll compare it to the graph that is less reversible. So you have this similar aspect, except now you have this cycle in here. So let's show you what this would mean. So like, let's say you're starting down here at, you have 1 degree of global warming, and then on the y-axis is something that you care about. Like, let's say it's, I guess, okay, if we're warming and it's going up, like let's say it's the amount of thawed ground in the Arctic. So you have permafrost, but the amount of thawed ground is going to go up as you're warming. So let's say you have global warming, and so you're increasing your amount of thawed ground in the Arctic by a little bit, and then you have a little bit more warming, and then all of a sudden you've initiated some type of a self-sustaining positive feedback And now you don't have to warm the globe anymore, but then you get this big change in the amount of thawed ground. So all of a sudden, now you have way more thawed ground, even though you didn't change your amount of global warming. So you cross some threshold, you have some straw that broke the camel's back. And then as you increase temperatures more, you are thawing a little bit more ground, but it's not nearly as dramatic. And so then this is the important part, is that if you go back, if you start cooling the temperatures again, in this case, you can cross the threshold on the other side and go back. So you, once you start cooling, then all of a sudden you're initiating your positive feedback in the other direction. And so then you are freezing a bunch of ground. And so you have a threshold, but it's reversible, right? And like, so that, like, a clear example of something that would not be like that is like if you kill an ecosystem or something, right? It's like you warm up, you warm up, you warm up. A coral reef would be a good example of this. You kill the coral reef, it dies off. Now, if you cool down, does a coral reef spontaneously come back to life? Like, no, it's dead, it's gone. So that's irreversible. But some things do have thresholds that are reversible. And then here would be an example of a kind of less reversible, is that you warm up, your response to something is changing, it's going up, you cross some threshold, and so then you get this big change in your response. And then if you start cooling, or so you warm more, and then if you start cooling, you actually don't cross this threshold in the other direction, at least at the same temperature. And then you're kind of stuck up in this other phase of the system. This is called a bifurcation. But the phrase that, the vocabulary word that we'll use in this class is hysteresis. So hysteresis is the dependence of the state of the system on its history. And what that would mean in this case is that depending on where you are in this cycle, you're going to have different values for your response of something. So if you're at 2 degrees of global warming, and you want to know where am I on my y-axis, where am I on my response, that will depend on the system's history, whether or not you're coming up down here on this trajectory, or whether or not you're coming back down here on this trajectory. And I'll show another example of that, which is clearer. But yeah, so in this case, it would be like you'd have to cool much more, and then you cross a different threshold to get back down here. And then you could start over on this component of your cycle. So let's do the same thing, look at the same idea of hysteresis, but with an actual physical example, something that we're familiar with. So let's look at the relationship between the amount of energy coming in from the sun. And I've just put this in here in arbitrary units. So it goes from 0.85 to 1.1. And then look at the relationship between that, the energy coming in from the sun, and global temperature. So we're going to start off down here where we have relatively low energy coming in from the sun at low global temperature. And then let's say we start warming up the climate by increasing the sun, the output from the sun. So the sun gets a little bit brighter. It goes from 0.85 to 0.9 units. So then the temperature is gradually increasing. And then we keep doing this. We get, so the energy coming from the sun now is at 1 unit. So a little bit more, the temperature is gradually increasing. Then we get to 1.1 units, we're turning up the sun even more. The temperature is gradually increasing as we're melting ice. But let's say now at 1.1, we've reached a point where the ice sheets melt becomes kind of self-sustaining, right? So we talked about the ice albedo feedback, where as ice melts, that means there's less reflective area, reflecting sunlight back to space. And so then more of that sun's energy is absorbed at the surface, which warms the temperature, which can melt the ice more. And so that means that at this point, you've reached a point where you don't even have to turn up the sun anymore. And now the global temperature dramatically increases because the ice sheet is just by itself melting away. And so then your global temperature spikes up without any change in the sun. And so then if you turn down the sun back down to 1 unit, the sun is getting dimmer, but it's too hot for the ice sheet to form. The ice sheet is not going to form because you're stuck up here with the temperature being too warm. And so this is essentially an irreversible change then. You melted away the ice sheet. Now you're stuck in a temperature that's too warm to get the ice sheet to come back, even if you turn back down the sun to this level of 1 in this case. And so this is hysteresis. So this means that the state of the system at any given time depends on its history. So global temperature in this case depends not only on the energy coming from the sun, but also on whether there's an ice sheet there or not. And whether there's an ice sheet there or not depends on the long history of what has happened in the past. And so this is interesting. Like if you remember from algebra or pre-calculus or calculus, you study functions in those math classes, right? And it will, when you study a function, it will say like y equals f of x. And so what that means is that if I give you x, you can give me y. So part of the definition of a function is that every single y value, or every single x value gives you exactly 1 y value. So like y equals f of x equals x squared means every x value that you put in there will give you 1 y value. But these, in the real world, we see things like this all the time where the actual thing that you care about is not a function of the forcing. And to like why that is because if I give you x, you can't necessarily give me y without knowing something about the history of the system. So if I give you x equals 1, you could say, well, y might equal 0.9 or it might equal 1.075. But so it's not a direct function of that. And so unfortunately, functions are less applicable in the real world than they are in math class. So hysteresis, the dependence of the state of a system on its history. So that was a example in climate science, but it's actually even more intuitive than that, I would say. So like a good example of hysteresis just in everyday life is the popularity of various things. So for example, the popularity of sports. So whether that's American football in the United States or cricket in India, these things definitely have hysteresis where they are popular because of some, a bunch of historical contingencies and accidents. And then they've reached some state where they're in this like self-perpetuating system, right? So it's like the sport is in the media a lot, and then there are many opportunities to play the sport. So it being in the media a lot means that there's going to be a lot of opportunities to play the sport, which means that there's public interest in the sport, which keeps it in the media. And so these things all kind of reinforce each other. And so like to bring that point home, like what if we were to take one of these elements out? So imagine we were to erase everyone in the United States knowledge or memory of American football overnight and then waited 50 years. And then you ask the question like, okay, would it reemerge? Is it just a product of like football being so intrinsically interesting that it would just have to come back in exactly the same form, even if everyone forgot what it was? And the answer is almost certainly not, right? Like it is where it is because of a bunch of historical accidents, and it's in this kind of self-perpetuating state, this kind of chicken egg state, but it's dependent on its history. for it to have gotten to that state. And so if you pull one of these elements out of its self-sustaining mechanism, it will probably collapse. And so it would be an irreversible change. This would be an example of an irreversible change to that system. And so, you know, other things that are popular, what about like celebrities? So this would definitely apply to especially certain celebrities like Kim Kardashian, who I don't know what her like job description would be, right? It's not like she's a singer or actress necessarily. She kind of is in this state that she's in this self-perpetuating state where it's like the person is in the media a lot, lots of people are exposed to this person, there's public interest in the person, and so then you have this situation where she's famous because she's famous, right? She has 161 million Instagram followers, and it's basically because other people follow her, right? Other like people want to know about her because other people want to know about her, and so she's in this self-sustaining state. So similarly, if we were to pull one of these elements out, so remove the public interest in the person, and were to wait 5 years, would Kim Kardashian spontaneously reemerge just as famous as she was previously? Probably not. Marco says she bought followers. Yeah, that would be a part of it too. Also, she's married to Kanye West, so that might keep her in the limelight more than someone else. But the point here is that if you were to take out one of these elements, like immediately have it where the person is not in the media all of a sudden, that kind of collapses the entire self-sustaining system. And so this happens with celebrities, right? Where it's like someone used to be very famous, and then all of a sudden they're kind of gone. They're gone from public spotlight, and it's kind of a mystery why. But it's like one of these things was pulled from their self-sustaining cycle. Okay, so that's all background and tipping elements. And so now I'm going to go kind of quickly through a number of tipping elements that we're most concerned about in the climate system. And so as far as the test is concerned, you're not going to be asked about like super specific mechanisms. This is I'm just kind of highlighting what are the major elements in the climate system that we're concerned about tipping, and some rough idea as to why we might be concerned about them tipping. So I'm going to go through 5 of these relatively quickly. So Greenland ice sheet disintegration. So 2 of these are ice sheets melting, which is not super mystery as to why, right? It's just warming and they start melting. Permafrost loss is another one with ice melting. And then we have a ocean circulation change. So the Atlantic Meridional Overturning circulation is a fancy name for an ocean circulation that might shut down or shut off, which would have some big consequences. And then Amazon rainforest dieback. So it's possible that the Amazon is essentially kind of a self-sustaining system, and it's possible that you could push that into a point where it tips over and basically the Amazon turns into a savanna rather than a rainforest. So first, let's go over these ice ones. So one thing about the Greenland ice sheet, if you look at the Greenland ice sheet from space, this is what it looks like. And this is with the sea ice taken away in the Arctic Ocean. But notice how lonely it looks. Notice what an anomaly it is, right? So it's this ice sheet sitting on the continent of Greenland. But you might ask, like, why is there not ice at the same latitude over here in Alaska? Why is there not ice at the same latitude in Canada? Why is there not ice at the same latitude in Northern Europe? And so what that is telling you is that the Greenland ice sheet probably has some self-sustaining aspect to it, right? And so it's only there because it is there, similar to American football and Kim Kardashian. So this is the simplified version of the self-sustaining aspect for the Greenland ice sheet, is basically that it's big enough, there's enough mass on the ice sheet for the top of the ice sheet to be high enough in the atmosphere such that it's cold enough for everything to fall as snow. So we talked about, you know, as you go up in the atmosphere, it's colder. And if your ice sheet is high enough, then that means all the precipitation falls as snow because it's cold. So even here, where we're at an elevation where temperature is above freezing, a lot of our precipitation starts off as snow in the upper atmosphere, and then it melts as it comes down through the atmosphere. But if you have an ice sheet that's really tall, then it's not going to have time to melt, and so it's going to fall as snow. So that would mean that part of this self-sustaining mechanism is that the ice sheet is tall enough so the precipitation falls as snow, and that means that there's enough frozen water, enough mass being accumulated at the center of the ice sheet to balance all of the melting that happens on the outskirts. And so if you were to pull one of these components out, if you were to say, okay, it's going to get warm enough so that the top of the ice sheet is now low enough in elevation where not all your precipitation is going to fall as snow anymore, and some of it's going to fall as rain, then you might initiate kind of this self-reinforcing feedback. Yeah, so as it warms, then the elevation of the ice sheet decreases, and so then it's going to warm more and melt more. And we talked about this may basically already be happening because we've been looking at ice mass loss from Greenland. And we talked about how it's down over 4,000 gigatons of ice just since we've been able to measure this with gravity satellites since 2002, where, to remind you, this is what a gigaton sized ice cube looks like compared to the Empire State Building. So losing a ton of mass. And yeah, so this means that we may have already essentially tipped this system into a new state. Like, it's definitely on a trajectory where if we were to stop global warming today, it's not going to get any warmer. That does not mean that the ice sheet is going to stop melting. So it's going to be continuing to melt. But then that brings up the question of like how long it takes for it to melt. And so that's part of this important difference between the Malcolm Gladwell type tipping points that are all about things happening very quickly in one abrupt moment versus climate tipping points where the crossing of a threshold commits us to a change, but the change itself may take centuries or longer to be realized. So just look at how long it would actually take to melt Greenland. So this is a graph of Greenland melt in terms of how much sea level rise Greenland would contribute. So global sea level rise. This is in meters. So just to remind you, a meter is 3.28 feet. And so look at the time scale here. This is the year 3000. The year 2800, the year 2600, the year 2400, 2200. So we often talk about the year 2100 in climate change projections. But if you're talking about melting Greenland, you have to go out, 1,000 years. So these are various emission scenarios that we've talked about. So RCP 8.5 is our high emission scenario. RCP 4.5 is our medium, and then RCP 2.6 is kind of like a meeting the Paris goals emission scenario, but they're almost stacked up on top of each other by 2100. You don't really see the spread emerge until well into this millennium. So, 2500 is when they're really starting to emerge. And yeah, so this is what Greenland looks like in the year 3000 under high emissions, under medium emissions, and under Paris Agreement type emissions. So we absolutely may be on the path to totally melting Greenland and increasing sea level by 8 meters. So in the 20s of feet just from Greenland alone. So that doesn't include sea level rise from thermal expansion or sea level rise from Antarctica. But we're not going to be seeing it in the next, several decades, and even by 2100, it's not super obvious. It takes a long time to melt these things. So, Greenland has been there for hundreds of millions of years, or the ice sheet has been there for hundreds of millions of years, and so they don't disappear in decades. So for each one of these tipping elements, I'll put them on our projection of global temperature. So our various fanning projections with different emission scenarios. So I'll show you where we might hit these thresholds and how long they might take. So I showed you this before. This is our pre-industrial temperature, global warming, where we are right now in 2020. Here's our 2 Paris goals. This is where we think current policies, if they were to be implemented as stated on the books, would bring us to in 2100. And so this is the Greenland ice sheet disintegration tipping point plotted on top of that. So basically, we think that we may have already crossed the tipping point. We're not really sure. And so it could be anywhere from 1 degree Celsius above pre-industrial, where we are right now, to 3 degrees Celsius above pre-industrial, so 2 additional degrees. But then the horizontal axis is how long it takes to actually transition. And so that's like centuries to millennia. So it's kind of good news, bad news. Definitely bad news that we may have already tipped that. We're not really sure. And I say we're not sure because if we were to stop emissions today, this previous projection kind of showed that you would maintain much of the ice sheet by the year 3000. But that's an uncertain projection as well. We're not really sure how strong these self-reinforcing feedbacks are. So the tipping point could be higher, it could be at 2 or 3 degrees. But then so that's the bad news. But then the good news is that at least you have centuries to millennia to deal with it. So whether or not you're thinking about dealing with it by moving people away from coasts, building seawalls, that would be adaptation, or if we figure out how to scale technology to pull carbon out of the atmosphere, then you could potentially stop the melting of the ice sheet by bringing global temperatures back down. So that's the Greenland ice sheet disintegration. So the West Antarctic ice sheet disintegration is very similar in concept. So one important thing about the West Antarctic ice sheet is that it's actually the bedrock that it lies on is underwater. So I'll show you what happens. So basically over millions of years, you have snow building up over the continent. So in this case, the continent of Antarctica. That snow turns into ice over the long term. So an ice sheet builds up because it snows in the winter and then it's cold enough for the snow to survive the summer, so that when it snows again the next winter, it just piles up on top of the previous winter's snow. And over millions of years, you can get an ice sheet that's over a mile, multiple miles in height or in depth. And so that's what happened, so much so in Antarctica that the ice sheet is so big that it actually depresses the continent. So the continent is now under sea level, and it's kind of like the ice is acting like the continent. And so that means that it's very precarious, because for sure that ice sheet would not be there if it was just an ocean. It needed that land to be above sea level in order for the ice sheet to build up. And so then if it starts melting, essentially what happens is this, so first this is a graph, or this is a map of the elevation of Antarctica underneath the ice sheet. So a lot of these glaciers, a lot of this, what you see from space, is sitting on bedrock that is now below sea level. And so that means that the ice sheet like Kim Kardashian, is only there because it's there. It's this self-perpetuating system. And if you were to delete it, if you were to pull out one of these elements, like the ice sheet not being tall enough so that precipitation falls as snow, then the ice sheet will kind of, go into this state of self-reinforcing feedbacks and melt itself and be irreversible on human timescales. So you wouldn't get it back by all of a sudden cooling temperatures to where they are now. This is the technical mechanism for what happens to the West Antarctic ice sheet is called marine ice sheet instability. And so that's basically this idea that as it starts to melt, more of the ice sheet, this grounding line it's called, is exposed to water that's above the freezing point of water. So as it melts, and since this continent slopes backward, it's called a retrograde slope. It's sloping backward into the center of Antarctica. As it melts, then more and more of the ice sheet is exposed to this water that's going to melt it more and more. And so that's just going to initiate this positive feedback loop. And so that's another major concern, is that we may have warmed up the temperature enough to initiate that positive feedback. And as we talked about a few lectures ago, again, with our satellite measurements of Antarctica, we see huge mass loss in this location, in this West Antarctic location. So down 2,000 gigatons, or this is a gigaton ice cube, down 2,000 gigatons on Antarctica overall, and most of that is concentrated in this, what's called the West Antarctic region, which is sitting on bedrock that's below sea level, and so very precarious, very potentially sensitive. So the same thing kind of applies here in terms of the timescales. It may be centuries rather than millennia that you would melt that. And the bad news is, again, we may have already crossed some threshold where that is essentially destined to melt in the long term. But it's possible that that threshold is not until closer to 4 degrees Celsius. So a lot of uncertainty with these. Okay, Amazon rainforest dieback. This is another potentially scary one. So first, this is where the Amazon rainforest is. So most of the Amazon rainforest is in Brazil, and then distributed amongst several other countries: Venezuela, Colombia, Ecuador, Peru, Bolivia. The important thing about the rainforest is the rain part in terms of the climate system tippiness of the rainforest. So rainforests require rain. And interestingly, rainforests produce rain. And so you can kind of start to get a feel for, okay, how might this be a self-perpetuating system? So just to put some more, to flesh that out a little bit, right? Rainforests require rain because of think about our photosynthesis equation, right? So all plants, they require carbon dioxide from the atmosphere, they require water from the environment, they require sun, they use that to make glucose stored in their plant tissue, and they release oxygen. So they need water. Okay, where do they get that water from? So the initial input is going to be, you have evaporation over the ocean, right? So you have the Atlantic Ocean next to Brazil, next to the rainforest. That water vapor makes it over land, over South America, where you have condensation and precipitation. So that's your input. And then we talked on Monday a little bit about evapotranspiration. So some of that water just sits on the ground and evaporates back into the atmosphere. A lot of it is transpired from the plants themselves, where the plants are taking the water in from their roots, and then it's going up their stems through osmosis. And then the plants release the water to the atmosphere. They they don't use most of it in photosynthesis. They just release it back to the atmosphere. And so that means that you're going to have a bunch more water vapor in the atmosphere than you would have otherwise, because that rainforest is actually there. And it turns out that 50%, so half of the rainfall in the Amazon, is recycled or regenerated rain that came through the plants themselves and was recycled back into the atmosphere. So much of the rain is only there because the rainforest is there itself. And so that means, again, we have this self-perpetuating system. The rainforest produces a great amount of evapotranspiration. The atmosphere produces a great amount of rain. These things reinforce each other. And so then the rainforest is essentially there because it's there. And so we can actually, here's an example where we can actually see this from space. So this is a picture of the Amazon from space. And so this would be, you know, your source of water is coming from the ocean, is coming over here. But most of these clouds, most of this water vapor is made possible by the plants themselves putting the water back into the atmosphere, where it's condensing and then raining and then reinforcing the rainforest system. So what could perturb this? What could happen? So it's possible that climate change will reduce the initial rainfall in the Amazon. So that would be a situation like this. So we talked about this map last time. This is the change in rainfall everywhere under a high emissions scenario in the year 2100. And we see that over the Amazon, there's not a strong signal, but the kind of middle of the road guess is that we would have a decrease in precipitation in the Amazon. And so that would mean essentially that we are reducing the amount of rain coming in to the system from the outside. And so then that could kind of cascade. If you have less precipitation initially, then you're going to have less evapotranspiration. And especially inland, as the rainforest typically kind of advects all that moisture inland, that could start causing die-off of the rainforest that way. So that's one mechanism. Another mechanism is that increased atmospheric CO2 itself actually makes the plants more efficient with their water. So it means that they have to open their stomata less, and they let out less water as they're doing their photosynthesis. And so that could actually decrease evapotranspiration, or could decrease transpiration. And so that would mean that you have less evapotranspiration, and so that could harm this self-perpetuating cycle as well. Again, I'm not going to ask you about like the details of these mechanisms. It's more the concept that you have something that's a self-perpetuating system, and that there's something about climate change that's going to pull out one of those self-perpetuating mechanisms, and so then can cause the entire thing to collapse. And then the third thing that could harm the Amazon rainforest is not really through climate change, it's through deforestation. So obviously, if you just cut down a bunch of the rainforest, and like I think 17% of the Amazon is deforested today relative to where it was previously, that makes the whole thing weaker, because you're going to start reducing evapotranspiration that way, and you're going to potentially cause positive feedbacks. You're going to potentially cause the entire thing to collapse. And so the more deforestation you have, the less warming you would have to have in order to tip the entire system into a new state. So the modeling on this shows that Amazon dieback could occur as early as about 3 degrees of global warming above pre-industrial levels, and it could be as high as 5 degrees. And then this is a little bit of a quicker one, especially compared to the ice sheets, that it could transition. It wouldn't just necessarily be, you know, a desert or a barren landscape. It would transition from a rainforest into a savanna type ecosystem. But obviously that would be incredibly detrimental to all of the biodiversity and life that is currently in the rainforest. So let's do just this one, or we have two more here. So one is this ocean circulation, the Atlantic Meridional Overturning circulation. And this is a ocean current. I think the most famous component of it is called the Gulf Stream. So we have warm water coming up from the south, and then part of that forms the Gulf Stream, and then part of that makes it up into the North Atlantic. That cold water then sinks and is transported back down to the south at depth, so near the bottom of the ocean. So that's why this says North Atlantic deep water. Deep water meaning that it's at the bottom of the ocean. And then this North Atlantic current is at the surface. And so this ocean circulation, what it does is it transports a bunch of heat northward into the North Atlantic. And the whole thing can be kind of thought of like a conveyor belt, right? And so you need this water here to sink and to go back to the south, and you need it to come back up at some point and then flow back to the north. And these are all connected just through conservation of mass, that you can't have one thing going without the other thing going. The whole thing has to be on, or the whole thing has to be off. And so that means if you were to change one part of this, so we think it's mainly driven, the whole circulation is mainly driven by the fact that you have a bunch of cold water sinking in the North Atlantic. So if you were to somehow make that water less dense and less able to sink, you might turn off this entire conveyor belt. So here's our self-perpetuating system. We have the import of salt, of dense salty water, colder water, or it's warmer, but then it cools down and sinks. We have this import into the North Atlantic, and then that is what causes the sinking of the water, and then it's all connected through this conveyor belt. And so we are worried that with global warming, either meltwater from the Greenland ice sheet or enhanced rain, that will cause more fresh water to be in the North Atlantic, and fresh water is less dense than salty water. And so that might make it more difficult for water to sink here. And so then it could turn off the conveyor. But then another concern is that it might warm here more than elsewhere. And so that differential warming might cause the density gradients to not be sufficient to cause water to sink here and thus maintain the conveyor belt. And so we do think that there is evidence that this is already happening. So if we look at trends in temperature globally, I've shown this a few times, trends in temperature globally from 1800 or 1880 to 2020, it's warmed essentially everywhere except in this North Atlantic region. And we do think that this warming hole is because the circulation is slowing down. And so you're putting less, you're advecting less heat into the North Atlantic. And so it's slowing down, has not shut off. But if it did shut off, this would cause a major cooling of the Northern Hemisphere. And so this was the premise of the 2004 movie, The Day After Tomorrow. In that movie, it happened in a matter of hours or something, where New York and all of Europe and everything immediately froze because of global warming. And this is something that's possible. So it just wouldn't happen that fast, and it wouldn't be as dramatic as this picture. But this is a map of the change in temperature that we would expect from this circulation shutting down. So we would have major cooling in most of the northern hemisphere. And so this would be happening as the Earth is getting warmer and warmer and warmer, and then this thing shuts down, and so then you have cooling relative to what you would have had otherwise. And then it's basically canceling each other out. That you have global warming from greenhouse gases, then you have cooling from this shutdown in the circulation. And they're on roughly the same magnitude, where you actually could return to temperatures previous to global warming. Whether or not that would be a good thing or bad thing, I don't know. I mean, this would be highly disruptive, and then you still have the southern hemisphere warming, and there would probably be a bunch of unforeseen consequences of that. But if you're primarily concerned about temperature itself, for whatever impact you were looking at, this actually would be something that would bring us back down in terms of temperature. So it'd be kind of a negative feedback on global warming anyway. So the modeling for that tipping point puts at about 3 to 5 degrees Celsius. So again, these are all like, you know, tipping points that we were either kind of crossing already, or they're within our choices of what we're going to be looking at for the remainder of the century, which means that they're within our choices of what we're doing right now, because our you know, energy infrastructure lasts for 30 years. So every coal power plant that we build now, especially in China and India, where they are building new coal power plants all the time, those are committing us to additional amounts of warming and potentially putting us on these paths that cross us into these potential tipping points. So the range here is 3 to 5 Celsius, and then we think that that would collapse on a timescale of about a century. So not in an afternoon like they do in the day after tomorrow, but a century is still quick on geological timescales. So I'm going to summarize these in this chart. So one thing I didn't get to, but I'll just tell you right now, is this idea of Arctic permafrost melt. So some people will kind of say that, oh, it's going to get warmer, and then that's going to start melting frozen carbon in the Arctic, and that will just amplify the warming further, and then it will just tip the entire system into a new state where you just have runaway warming. When we look at that in detail and we look at the modeling of that, we really don't see that. So we see that as it gets warmer, there will be carbon released from permafrost and from methane hydrates and clathrates, but we don't see that as a self-perpetuating, self-amplifying feedback. So it's something to be concerned about in terms of how much warming we get, but we're not concerned about it in terms of it being a tipping element that goes into a new state. But the rest of these, Greenland ice sheet melt, West Antarctic ice sheet melt, as well as this ocean circulation and rainforest dieback, are coming up here potentially this century if we haven't already crossed them. And then they do take longer than we typically think about with a tipping element, but this is still abrupt on geological timescales, and it could have very large consequences for a number of things. So, you know, putting these two together is 12 meters of sea level rise. So, you know, getting near like 30 feet of sea level rise, like even though that's over centuries to millennia, you think about, you know, the pyramid of Gaza was built like 4,000 years ago. So it's weird for us to think on timescales longer than a decade, but hopefully there's going to be people around and they won't be very happy with us if we totally reshape the global coastlines from just our actions over these current decades. And so one thing I put on here along with that is energy transition. So there could be a tipping point in moving from fossil fuels to, you know, renewable energy or energy systems that don't release carbon as a byproduct. And so that would go back to the Malcolm Gladwell type tipping points, where you have some type of a social or political contagion where an idea takes hold, and then we actually get a transition into action on that level. So I just put that on here as perhaps maybe the most relevant tipping point that would be potentially activated in the next over the next decade or two. So this was not an exhaustive list, and I'll just show a map from another paper of other potential tipping elements. Again, going back to that original theme of the paper, these are very speculative. They're kind of cloudy and foggy as to where they might be and whether or not they might exist as actual tipping points. And a lot of these even have just, question marks on them. But, the more we warm, the more we might get surprises and have something kind of blindside us, something that we weren't necessarily thinking about, or something that we thought was far off into the future, but then all of a sudden shows up. So it's something to be concerned about when you're thinking just about risk management.